let's do some. First, let's begin at the end of the last class. Let me carefully go through the thing. I watched the clock ticking and I was like, I must go faster, which is about the worst way to teach math, is to like compress it. So let's start from here. Let's start where we were before. So let's remember that what we were looking at was this integral. I think it was 2z plus 1 over z squared plus z dz. And the contour that we were integrating over was modulus of z is equal to 2. So we're going to do this integral again, but carefully. And all the questions about orientation and the missing terms will be answered because I will do it correctly this time. So the basic idea was, first, we looked at this. We'd really like to use the Cauchy integral theorem if we can. Remember that the Cauchy integral theorem says that 1 over 2 pi I times the integral around some contour C of f of z over z minus w dz is equal to f of w when w is inside C. So values on the boundary tell us what's going on in the interior. So we're going to try to use that theorem to understand this problem. So I think last time we pointed out that this thing has two asymptotes. Z is equal to 0 and z is equal to 1. And I think I've gone so far as to try to construct a contour that would allow us to use that theorem. So the basic setup here was that we had an asymptote at 0, and -1, not +1. An asymptote at -1, so there's z is equal to 0, and there's z is equal to 1. The last time we solved this problem, the way we did it was we used partial fractions to break this up into two pieces, and then we used the circle contour theorem twice. This time, we're going to try to do it all at once. So our original contour looks like this. 1, 2. So here's our original contour. Barely visible, of course, because why should these pens work? They should make these toxic again so they work. That's the, oh my god.
I have one of yours, actually.
No, I have a red one.
I have the red one, I think you gave me.
Yeah. Okay.
Return.
So, this is our original contour C. Right, so we're integrating over C, where C is the circle of radius 2. And so what we're going to do is we're carefully going to construct a new contour. And what that contour is going to look like is paying attention to orientation so we make sure we're on the left. We travel around the contour C, and then we come in to this singularity right here. And we want to avoid the inside of that, so our area has to be to the left. So the first thing we're going to do is come in this way so that the area that we want in the interior is to the left of that contour. I think I called this L in last time. And then we go around this way, because to the left is the area that I'm trying to simply connect. So I can call this C0. It's the bottom half of a circle that's going to go around Z is equal to 0.
So the first step is you do go around C counterclockwise.
What's that? Yeah, this is the integral that we're trying to compute, and the area that we're going to be enclosing is inside of C, and we're going to split it into like one piece that kind of wraps around like this, so that it's simply connected. The goal is to create a simply connected region so I can apply the Cauchy-Goursat theorem. So I have to orient the curve. I have to orient the curve so that all of the interior is on this side of it. That's kind of what the goal is. I want to simply connect the inside. So I come around C0, I have this other little linear piece right here, which I called M in, then I wrap completely around Z is equal to 1, going this way so that the area is to the left. Then I come back on that same curve, this is M out, then I go around the top half of C0, headed this way, and then I go back out on L. So the interior set here is simply connected. The function is analytic on that set and through the curve, because there's only two places where it's not, so it's simply connected and analytic through it. Yep?
So you can use the Cauchy integral theorem on this, because you're making the circles around each asymptote arbitrarily small.
Yeah, I mean, the idea here is that it doesn't matter how small I make these circles, right? It's really what I'm thinking of is that this. So secretly in the background, the way to think about this is that I'm approximating this loop with something that's slightly inside it and then limiting out to it, right? But these circles can be whatever I want. Because as long as I'm inside the big contour C, these two circles can be any size you want as long as there are circles around. So I just need to be able to find a circle that sits in around that singularity. Yep.
Is our goal to exclude the area with the singularity?
So what we're going to do is, so this is like so what we're going to do is we're going to write down an expression for these integrals. And then we're going to notice that the integral over the union of all of these things is 0. That's the first thing. But the individual pieces, well, the thing we're interested in solving is the integral around C. That's our unknown, is the integral around C, right? But I do know that the integral around C naught in this direction is the negative of the integral around C naught in the other direction, which reverses the orientation, but also flips the area, right? That's just the rule of integration, says that the integral of going around a contour in one direction is the negative of going around it the other way. So we're going to cheat, basically, and say by flipping the orientation, I can compute the integral on the interior of C naught. This is C naught in the backwards orientation for the integral if I was going around that singularity. Okay? So the assertion here is that the integral, if I call S the union of all of these things, right? So what is S? S says do C and then go in on L. And then, so we go all the way around C, and then we go in on L, and then we go around the bottom of C0. I'm calling it C0 because it is the contour around the singularity at 0. And this is C minus 1 because it's the circle around the singularity at minus 1. So if I do C in on L, the bottom of C naught, and then I do M in, and then I go around C minus 1. Both of these, of course, not in the counterclockwise direction, but clockwise. This is also clockwise. And then I go out on M. And then I do the top half of C0, but in the clockwise way. Does that get me back out again? Oh, and then I do L out, right? So I have to do all of this stuff. Now, when you get used to these, you don't have to write all these pieces down because a lot of them just instantly cancel, right? Every one of these L outs and L ins are negatives of each other because you're doing the same integral but on reversed orientations. It's the same path but backwards, right? So the claim is that the integral of f on S is equal to the integral of f on C plus the integral of f on L in plus the integral of f on all of C0 but backwards. I can do that because I did the bottom of C0 and the top of Z0, so I can use integration theory to just say, well, if I've got two pieces, I can stick them together and do one contour instead. I have this piece and this piece. Who cares when I did it? All together, I went all the way around. And when I say backwards, it means because I'm crawling around the singular point in the wrong orientation for that integral, right? This is the reverse orientation of the integral around C naught. If the other way to write it is you could put minus C naught here, because minus C naught says that you're going around C naught but the wrong way. The positive orientation goes around an interior set in this direction. The negative orientation goes in the other way. Then notice that flips the interior and exterior as well, right? Because going in the backwards direction puts the other side of the curve on the outside. Okay, so I do L in, I go all the way around C naught, but backwards. I do I do M in. I do all of C minus 1, but backwards. And then I do M out of F and L out of F. Does that make sense so far? I have invoked no theorems yet except a basic structure of integration, right? I built a contour, I've decomposed it into pieces, and I'm saying the integral on the whole piecewise thing is equal to the integral on the individual pieces. The Cauchy-Gaursat theorem says that this is equal to 0. I've got a simply connected region. The function is analytic on it with a simply connected interior. I can assert that the Cauchy-Gaursat theorem says that this is remember, we've lifted the condition on simple closed curves, which if you're wondering about this intersection over here, any closed curve has this property. So the Cauchy-Gaursat theorem says, since we connected the interior up to be simply connected, that has to be 0 on the boundary. If Function's analytic in the interior because there's only 2 places where it's not. So now what can we do with it? Well, now we have an equation where the thing that we're trying to solve for is right here. That's our unknown that we want. But I have 2 integrals that I know how to do, right? I know how to do this integral and I know how to do that one if I reverse the orientation. So what I do is I write, okay, well that means, let's add these to both sides. Minus the integral f of minus c0 minus the integral around c minus 1 in the backwards direction of f is equal to the integral of f around c. L in and L out are the same integral but in opposite directions, so they cancel. M in and M out are performed on the same line in opposite directions, so they cancel. So we eliminate this and this and this and this because they're equal but opposite. This is what makes, so what I did was I subtracted this and this from both sides. So now I've got an unknown that I'm interested in. Again, this is my unknown here. And 2 integrals that I claim we know how to do. The first observation is that the minus of a negatively oriented contour is a positively oriented contour. So now we get the equation, the integral around c of f is equal to the integral around c1 of f plus the integral around, sorry, minus 1, and the integral around c0 of f. Now these are both positively oriented curves. But this is a much easier situation because this integral is performed like this. Here's minus 1, there's a little circle around it. Where this circle you can think of as being minus 1 plus re to the it, if you like. You don't even need that because we're going to use the Cauchy integral theorem to calculate that. And this integral is performed around this circle, where this is 0 plus re to the it, for possibly a different r, but the idea is this parametric integral, this parametric circle, and this parametric circle, those fit the requirements to use the Cauchy integral theorem. Why? Because f is analytic. Well, we're going to use this theorem, so let's start with, what should I erase here? This may be the original problem. That never hurt anybody. All right, let's just imagine we were doing just this integral by itself in a vacuum and we knew nothing else. So what are we doing? The integral around some small contour that contains negative 1 of the function 2z plus 1 over z squared plus z dz, and minus 1 is inside c. Right? That integral right here, that's the situation we're in. So this is that trick where you can resort this, where it looks like 2z plus 1 over z plus 1. Because this function is analytic inside here. That function is analytic on that interior, right? There's no singularity for that point in that little disk. And that means I can invoke this theorem. That function is analytic. The denominator contains the singularity. And so the Cauchy integral theorem says, this is the Cauchy integral theorem, says that this is equal to 2 pi I times this function evaluated at that center. Minus 1 is in the interior of the circle. The Cauchy integral theorem says that this is 2 pi I times 2 times minus 1 plus 1 over minus 1, which is 2 pi I. So I've reduced the problem. Without using partial fractions, I've essentially basically played the same game, right? So that integral, this one, was 2 pi I. What's the other one? Well, it's not going to be surprising. It's going to turn out to be some multiple of 2 pi I as well. So the picture for the other one is that the integral around c0 of 2z plus 1 over z squared plus z dz. Well, c0 is this picture. There's c0. There's this point in the interior, which is 0. But if I take this function and I sort it so it looks like 2z plus 1 over z plus 1 over z, that function is analytic. And 0 is on the inside of the circle, so I can invoke the Cauchy integral theorem to say that this is equal to 2 pi I times 2 times 0 plus 1 over 0 plus 1, which is also 2 pi I. So this is also by the Cauchy integral theorem. And the conclusion is that the integral that we were interested in, the integral of f around c, is equal to 2 pi I plus 2 pi I, which is 4 pi I. Okay, so that's like an application of how you use this sort of trickery and complicated contours to attack integrals that you might not know otherwise. Now, you don't actually need to go this long process that we walked through here in order to do all this. You actually don't need to do all those steps. So let's see if we can find one where we could actually write the answer down without grinding our way through all this stuff. So we're going to start with a function, and then we're going to write the contour down. But from the contour, we're just going to be able to say what the answer is. So the trick to complex analysis is seeing places where there is efficiencies to be gained. There's some business speak for you. So let's gain some efficiencies. Change the paradigm. Okay. Questions about this before I do the next one? It's important that you understand what we did here, because in the next one I'm going to skip some steps because you know there's pieces that turn out to not count. The L in, the L out, the M in, and the N out contribute nothing to the state of the problem. Okay. So let's look at something with a cubic. I mean, the point is to make these things painful enough that you don't really want to do them with integration by partial fractions. Unless you love computing coefficients, I guess is the... All right, so let's look at this guy. How about the integral around a contour C of the function 2z squared plus 1 over z cubed plus z dz, where we have the contour of radius 2 centered at 0. Okay, f of z is 2z squared plus 1 over z cubed plus z, which is the same as, yeah, z plus I, z minus I. So this function has 3 singularities, and all 3 of them are inside that circle. 0, I, and minus I. And the circle looks like this. Let's call that C. So let's draw the curve and see if just on the basis of the curve we can figure out what we should be doing here, without doing all the computations we did before. What should the contour look like? You go around C, then you can pick how you want to come into this thing. Like, it doesn't matter. It's, yep. The top is probably the easiest, most intuitive way to do this is to try to orient your ins and outs on the same line the singularities are. But really, it does not matter, right? You want to come in over here and do a circle around I and then come back out and go like this way to get around to 0, you're welcome to do so as long as you go in and out on the same line. It won't matter, right? Because you're going to go in on this line and you're going to come out as long as you simply connect the set when you're finished. It does not matter. The reason that we're using straight lines is because it's easier to envision what's happening. Okay, so here's the most natural contour I can think of for this. You do C by going around. You come down, making sure that the interior of your set is going to be to the left, so you should come down this way, and then go around I this way, and then you do this stretch, and you come in and go around 0, and you're still going this way so that your interior of your simply connected set is to the left. You go all the way around minus I, and then you come back. Right? Okay, now, all of this nonsense, you can already tell me what the answer is here. You can write down the integral that's going to solve this without doing any of the intermediate work if you think about it. All of the integrals on the in and out straight paths are going to cancel away. They're not going to be there in the final answer. The total integral, since you've made this into a simply connected set, the total integral is going to be 0 again by the Cauchy-Goursat theorem. So One assertion that you might be tempted to leap to is that if you didn't care about showing your calculus professor or your complex analysis professor that you knew what you were doing, you might just immediately write, okay, what's going to happen when all the dust clears is I'm going to get the integral around C of f is equal to the integral around that little circle that goes around minus I of f, and the integral around that circle at 0 of f, and that integral around C positive I of f. The dust is going to clear, that's going to be what falls out. Okay, but each one of those contours isolates one of the singular points of that function. So this is going to be equal to the integral around Ci of 2z plus 1 over, okay, so we're around I, so we have to get rid of the minus I term, z times z plus I all divided by z minus I dz. And this is going to be an integral around C0 of 2z plus 1 over z plus I, z minus I over z dz. And this will be an integral around c minus I, 2z plus 1 over z times z minus I over z plus I. Why did I arrange it that way? This function is analytic on the inside of that set. This function is analytic on the inside of that set. And this function is analytic on the inside of that one. That lets me apply Cauchy integral theorem 3 times. So the idea that we're building here too, where it's 2 pi I times the value of the function, that's like, that's going to be formalized in something called the index theorem eventually. Yep.
This might be a silly question, but is there like a physical analogy for singularities? Because when I imagine like the path integral, I imagine like walking around on a mountain.
Yeah, so in complex analysis, singularities are weird in complex analysis, like extra weird. Like, for example, there's this theorem that we'll maybe get to eventually in this quarter, and definitely next one if we don't, called the Great Picard theorem. Not named after Jean-Luc Picard of the Star Trek or the Starship Enterprise. That says that a complex function near an asymptote like this takes on every possible complex value in its range on any set that you draw around that point. So no matter how small the disk you draw around this, the function takes on every single complex number with the exception of 1. So it's like a hyperasymptote, right? A real function, asymptotes, what can the function do? Well, it could go to infinity or down to negative infinity, but it's real numbers. Those are easy to attain, and they can both go the same direction. Complex functions near asymptotes take on every single possible complex number. Certain kinds of asymptotes, I should say.
So no physical analogy.
I mean, no, it's hard. It's hard there.
Yeah.
Okay, so what does the Cauchy integral theorem say? It says this function was analytic on that disk, which contains that point, so I can write 2 pi I times the value of this function at that point, 2i plus 1 over I times I plus I, plus 2 pi I times the value of this function at that point, 2 times 0 plus 1 over 0 plus I times 0 minus I, plus 2 pi I times the value of that function at that point, 2 minus I plus 1 over minus I times minus I minus I. And if you like, you can work out the exact multiple that happens here. But notice, this actually means that these integrals are actually, they're pretty predictable, right? Because they all have 2 pi i's in them, and they're all multiplied by the function evaluated at those points. There's a couple of obvious questions you might ask, like, how come you've only ever showed us points where there's degree 1 singularities, right? I mean, I very carefully only showed you examples where all the places where the function was analytic had order 1. The answer is, we got to beef up our theory a little bit before we can handle asymptotes that have order 2. So anyway, this is typical of these sort of contour integrals, right? You write down the contour integral, you simply connect the interior of your set, apply the Cauchy-Goursat theorem, and that always will let you get something like that in this case, where there's order 1 singularities. A lot of the problems I'm going to assign you on this are going to require that you draw that contour, you should get used to it. Practicing drawing the contours is a really good way of getting ready for basically the rest of the class. Okay, questions about this? Anything I can answer? This is bad. You're gonna do a lot of these. I'm gonna give you, you should do a lot of them. I'm gonna give you like 2 or 3 to do, and then if you're really excited, just keep doing them. What's that?
So like you were saying earlier, if you decided to make it kind of like more complicated and take some weird like diagonal line
As
path,
long as it's
still
simple.
the same in and out cancel.
As long as you're coming in and out on the same path and you are simply connecting the domain, then everything's okay. So if you want to do the same problem, but you're coming in like, oh, I'm going to go over here first and then go around this circle this way, and then maybe I'll come out over here and come around this one, go over here and I do this one. As long as your orientation is correct, it doesn't matter how you get in and out. Yep.
So is there any collection of like holes and poles that you couldn't just draw circles around?
Yeah, I mean, so the problem is, so the answer is, what are you saying poles in here? We don't know that word yet. Singularities, asymptotes. Yeah, poles are coming. We'll get poles in just. We're right on the edge of actually defining what it means to be a pole. Yeah. So if you're curious, the word pole just means that you have an asymptote of some finite order. So like if I could divide a function by z to the 8th and still get like if you have a, how do I even say this? If you divide the function by z to the 8th and then it turns out that you have a removable singularity, so just a hole, the basic hole in the function, that's what we mean by a pole. So we'll formally define that when we get there. But there's a whole class of these asymptotes. So the answer is, for a finite number of them, you can always do this. Now, if the order is not order 1, it gets more complicated. And if you're trying to study a different kind of integral, it also gets more complicated. But yeah, basically this art of drawing around these things is like the reason this works, and that physicists decide they liked it was because you can do this with like sort of a standard approach. Yep.
How do you know which direction you're doing?
So the idea is that like when you draw the set, like this, and you say, okay, where's the interior of that? Well, the interior is, say that we'll put some asymptotes in there. The interior is the inside of the circle, right? Now, I don't need to pick an orientation. I can just draw a curve that goes all the way around these first. Like, okay, so you do this, I come in, I do this, I do that, I come out this way, and I get a contour, right? When I orient the contour, I just need to make sure that this interior is to the left of the direction that I'm traveling. So as I'm traveling along, I better see the interior to the left. We've, by convention, decided that's positive orientation.
Okay, so that's why the circle as a whole is going.
That's why this goes this way, because what it sees is the interior to the left, and then when I come down this path, it has to see the interior to the left of the direction of travel. Yep.
When you say order, do you mean like if you had like a z squared?
It would be order 2. Yeah. Yep. Every question you've asked me that you've prefaced with potentially silly has been devastating. So please devastate my mathematics with your question.
Can you do it with countably infinite order 1?
Okay, as soon as you have what's an infinite order singularity, you have something called an essential singularity, right? And essential singularities are way worse than these. Rational singularities and essential singularities are categorically different. And so I guess it's not totally letting the cat out of the bag to say, like, what you can do with rational singularities is you build a Taylor series, and then it has terms that stick out the other side with negative powers. And the number of negative power, yeah, if you've never seen that before, right? So if you actually wrote down a power series for something like, so you could write down basically if you write down a power series and there's an asymptote, a pole, or a singular point in the function that you wrote down, and it was rational, the degree, say that you're expanding around 0, and there's a 1 over z squared in the function, the series actually ends up with 2 extra terms stuck onto the end with power -1 and -2, right? So you have this kind of rational looking bit stuck on the front, and then a whole lot of Taylor series on the front, for the rest of it, which is called a Laurent series. If you have something that has countably infinite, countably infinite at the same point, if there's a singularity where they're essentially infinitely stacked up at one place, you get functions that look like this. So that has a singular point. but it's a singular point that cannot be expressed with some sort of rational thing. This has like an infinite order singular point. This is terrible. In fact, this is so bad it's called an essential singularity. There's no way to get rid of it. Now your question was, can you do, I'm not thinking about your question, what you're saying is, could you build up, say, a product of rational functions that converge, but there was an infinite number of them, where you just paste infinite zeros everywhere? To which I will say the answer is yes. You absolutely can do that. And what happens is, if the function is going to be analytic, those can only accumulate at one point. So if you have, like, say, here's how awful this situation is. We're talking about a function where you've got some disk where you're trying to, like, study it. And you start writing down the asymptotes. And the asymptotes get closer and closer and closer and closer and closer to some point. And there's an infinite number of them. And yeah, these are, so I'm going to point you to a type of function called a Blaschke factor or Blaschke product. And what you're asking about in particular can probably be thought of as an infinite Blaschke factor or product. So these functions are rational, but they're better than rational. These are rational functions that are strictly of size 1. They map the complex unit disk into itself. But you can multiply these together infinitely, and you end up with countable numbers of zeros smeared out all over the place. And they're analytic and have infinite, countably infinite singularities, and they're an incredibly interesting class of functions to study. We'll get there eventually because these are rational functions, but yeah. Yep.
I just have a question about math in general.
Sure. Oh, no. All right, philosophy time. Sweet.
It's not a bad question. It's called a rational function because it's got a numerator and denominator, but it doesn't have to have rational numbers necessarily in its domain or output.
That's right.
Why? Why come rational?
Well, I mean, so like the original motivation for rational, I mean, I don't actually know the etymology of the word rational, but aping the structure of the rational numbers, right? So a quotient of polynomials is the next algebraic extension of a quotient of numbers, right?
Sure.
So that, I mean, that's why they call it that. Now, okay, if you want to go like big time math on me and say, why do they, what about the rational numbers? I will remind you that the rational numbers are dense in the reals, so you never actually have to work on anything but the rational numbers. And actually the rational coefficient complex numbers are dense in the complex numbers. So if you really decide that you hate continuity so much that you want to have a set of like rational numbers that you're going to study your functions on, you can actually build an entire theory of calculus out of just rational numbers. It's kind of a nightmare because you have to include the limits of all the Cauchy sets, or the Cauchy sequences all over the place. But you can do it. You want to restrict these to rational inputs and outputs? It would be the rational functions.
Okay, I'm okay with that.
I mean, the real numbers are just a convenience, right? Most of the time we're working on the rationals anyway. We're just pretending that we're working the reals because what the hell is a real number, right? A limit of a sequence of rational numbers. That's the very first thing you do is say, oh, well, I don't know what it is. Approximate it with sequence of rationals, right? Okay. So let us first talk. So I said last time I wasn't supposed to be a threat, although I got some looks from people like, oh my God, what are you talking about? When I said that we have sort of arrived at the end of the easy part of this class, this is sort of the key. This idea is the key that unlocks everything else. The idea, it doesn't seem like it because the Cauchy integral theorem is so innocuous looking, right? I mean, seriously, 2 pi f of w is equal to 1 over 2 pi I integral of f of z over z minus w is the key that unlocks the rest of complex analysis, but it absolutely is. And we have a big fork in the road right now where there's 2 gigantic results that we can prove. One of them is gigantic for complex analysis, and one of them is the fundamental theorem of algebra. So what does the fundamental theorem of algebra say? How about the complex fundamental theorem of algebra?
Every polynomial factors into a linear term.
Okay, that's a consequence of the fundamental theorem of algebra. The way the fundamental theorem of algebra is actually stated is every polynomial, every complex coefficient polynomial has a 0. That's the statement of the fundamental theorem of algebra. If every polynomial P of z, and I should say we're doing the complex version. Every complex polynomial P of z has a 0, which means there exists some number c in the complex numbers so that P of c is equal to 0. The implication of that, and an immediate implication of this, is that every complex polynomial factors as a product of linear terms. It's one of the foundational properties that polynomials have. The real fundamental theorem of algebra says that polynomials factor as linear terms in irreducible quadratics. The complex version of it, which is better, because everything in complex is better, says that every polynomial factors into linear terms, but then of course the Galois theory says you're not allowed to know what they are. So this is called the fundamental theorem of algebra. It is one of the major results that we are going to prove. And it might be sort of weird to think that the fundamental theorem of algebra, which is absolutely an algebraic statement, to say that a polynomial factors is to say something about the ring of polynomials over the complex numbers, right? This is an algebraic statement that is used all over algebra, but the proof of it is entirely complex analytic. The most natural proof of it is complex analytic. So one big branch that we are going to do is we're going to build up a set of tools that sort of surprisingly actually is going to show the fundamental theorem of algebra holds. That's one set of tools. And all of those tools are the first, that's sort of the second major consequence of the Cauchy integral theorem, is that everything that leads up to that holds. The other one is, so this is sort of, I'm going to call this path 2. We're going to do this second. So the second chain of results is going to lead us to the fundamental theorem of algebra. The first path is we're going to say that F holomorphic implies F analytic. And that is a quite shocking result, that with no additional conditions, being differentiable once means you have a convergent power series with an absolutely well-defined maximal radius of convergence, depending on what center you choose. Yep.
Sorry, so PC equals 0 and PZ? Is that what
Oh, sorry, this is the end of this statement, right? So that P of 0 is equal to 0. And the implication, you actually can prove this using a pretty slick argument that, like, if you have a 0, then you must decompose entirely. It's like induction mixed with the division algorithm. Yep.
Shouldn't that be P of C equals 0?
Oh, P of C. It was supposed to be C. There exists a C and C. So yeah, it was a C, and then I completed into a 0 for some reason. Yeah. I closed it up with a contour. Okay, now this holomorphic implies analytic is actually quite, if you think about like what we're saying there, we're saying all together that to have one derivative implies that you have infinite derivatives, and that somehow you can use those derivatives to construct a uniformly convergent power series, just on the basis of one derivative existing. One derivative implies infinite derivatives and uniformly and absolutely convergent power series. I just finished waving my hands at this in Calculus 3, right? Where you like show people what the Taylor expansion is, but you don't prove why it works. You just say, oh, look, there's this thing called the Taylor expansion. So this is called Taylor's theorem. So that's our second big pathway, is to get to Taylor's theorem. And the third, I don't know if you guys have looked ahead in the book, but the reason why there's so many paths here, the next chapter, so chapter 2.2 is called Cauchy's integral theorem, and the next chapter is called Top 10 Facts About Cauchy's integral theorem. Path 3 answers the following question. We know that if f is analytic, if f is analytic, then the integral of f around a closed path is 0. We know that's true. An analytic function has these path-independent line integrals, right? The Cauchy-Goursat theorem holds. So if analytic, then the integral around closed paths is nothing. What about the other direction? What if I knew that all the path, so with conservative vector fields, this characterizes conservative vector fields. They are the same condition. To be conservative is to have path-independent line integrals. It's an if and only if. We've only shown if-then here. If analytic, then the perhaps less than surprising conclusion that like this sort of conservative vector field Green's theorem thing holds. So the converse to this is a beefy theorem called Morera's theorem. And that's going to say the opposite. If every path integral, if every closed path integral is 0, then the function must have been analytic. That's an incredibly useful thing to have at your disposal. Okay? So this is sort of the big picture of the three things that we're doing. So it's going to seem like we're just blasting through all this high-level mathematics all of a sudden here. But the idea is this is the place where complex analysis is really born. All of the structure of analytics now basically erupts from the Cauchy integral theorem. Yep.
It's just more of a curiosity, but is the complex analytic way of proving the fundamental theorem of algebra like the only way? Or
No, there's like a million proofs of the fundamental theorem of algebra. It was the first proof, though, I think. Cauchy proved it using this. It takes a lot more machinery to do it with number theory. Yeah, I mean, I don't know if anybody's ever pointed out to you, but like modern number theory is born from complex analysis and has complex analysis all over it. So there's this entire study called analytic number theory, which is the old kind. Algebraic number theory is new. Analytic number theory, which grew out of complex analysis, is old, like a couple hundred years old at this point. So complex analysis is one of these glue fields that connects all kinds of other fields together. Okay, so let's do one last result today, which I will leave to you to prove, which is our first move down the road to proving Taylor's theorem. All right, somebody tell me the Taylor theorem formula again. It's been a while since we've run on the board. What is a Taylor series? If I say something as a Taylor series, not a power series, but a Taylor series, what am I saying? F of z is equal to, I'll write the easy part. There. Oh, there's an n factorial down there. That's nice, okay. All right, so that's one contribution to the whole here. Z to the n. Z minus a, because we have some shit. We don't want to have our power series centered at just 0, right? This is not Maclaurin series. Maclaurin, who like wrote a textbook or something that had the Taylor series with a equals 0 plugged into it, and got a good series named after him.
Something like that.
All right, what's missing here? The nth derivative. Okay, so f n at a. The nth derivative of f evaluated at a. This is kind of where we want to go with a Taylor series, right? So if a function is analytic, so let's actually write this down real quick here. So this would be the same thing as saying f at a plus f prime at a times z minus a plus f double prime at a times z minus a squared plus the third derivative, I forgot a 2 factorial down here, at a 3 factorial z minus a to the third. If this is equal to f of z, this is what I want. I want some way to use the machinery of integration. So this is going to be weird because we're going to use integrals to find derivatives. And the reason that we can use integrals to find derivatives is because Taylor series are built out of derivatives. So we're going to motivate it, and then we're going to back in our way to a proof using the Cauchy integral theorem. Notice that we've been doing computations that look like this. F of z is equal to c naught plus c1 z minus a plus c2 z minus a squared plus c3 z minus a to the third, and so on. We've been doing these. Oh, that's terrible. Barely legible. F of z C naught plus C1 Z minus A plus C2 Z minus A squared. This is just a general power series, right? And we already know, I actually pointed the next thing I'm going to say out last time. I know how to integrate both sides of this and make sure that something non-zero pops out. If I just integrate this, I get nothing, right? Pick a contour, make the function analytic, integrate both sides. The Cauchy-Goursat theorem says 0 equals 0. Wow, okay. If I want this to not be equal to 0, the sort of intuitive idea is let's take everything and divide by Z minus A. And then we ended up with f of z over z minus a was equal to c naught over z minus a plus c1 plus c2 z minus a, and so on, right? If I integrate this, that part turns into c naught 2 pi I, and everything else turns into 0. That's what the Cauchy integral theorem says, right? The only one of these that survives is that one. We've done this a bunch of times now. Well, that tells me f at A. If there was a Taylor series, knowing C0 would tell me what f of A was, supposing I was too lazy to plug in f of A. What can I do to this setup that would let me calculate C1?
Z minus A squared.
Oh, okay, so if I put a Z minus A squared right here, then I would end up with this expression. I'd have the integral of C naught over Z minus A squared plus C1 plus, C1 over Z minus A plus C2 plus C3 times Z minus A, and so on. And by direct parameterization, anytime these integrals have a power of Z that's not -1, they're 0. This is 0, this is 0, this is 0. The only thing that survives is that term. And what you end up with is the integral of f of z over z minus a squared dz is 2 pi I times c1. But what is c1 according to our intuition from Taylor's theorem? c1 is f prime of a. These are equal, they have to line up, right? C naught has to be f of a, and C1 has to be f prime of a, and C2 has to be f double prime over 2 factorial, and so on. Each one of these things that we can pop out using this idea corresponds to a derivative of the original function. So, the first statement of what's called Cauchy's integral theorem for derivatives says, if you finish this up, what it says is 1 over 2 pi I, and then, so what was C1? C1 is equal to f prime at a divided by 1 factorial. So 1 factorial over 2 pi I times the integral of f of z over z minus w squared dz is f prime prime at a. Sorry, f prime of a, f prime. So if I'm willing to divide by a second power of z, what I recover is the derivative of an analytic function. And there's no reason why I couldn't keep dividing by higher and higher powers, which is going to give me a way of recovering any coefficient that I want. What am I going to divide by if I want to get C3 out of this thing? Z minus a to the 4th, because I have to leave that z minus a in the denominator so that it integrates to something instead of nothing, right? So after we're through with the exam garbage, we will come back and we'll restate, it's a necessary evil. We'll restate this, but I want you to think about how weird it is that we are calculating derivatives with integrals. Okay? Complex analysis is backwards. Anyway, and this idea of recovering the coefficients is how we're going to build the Taylor series. All right. I'll be in touch on Canvas later tonight.